That's what you don't want to do. Yeah. It'll be okay when I'm. Okay. Are you ready? I now call to order the Society's 2,398th meeting in the 148th year since its founding in 1871. Good evening, everyone. Okay, my name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Charles Norton in the John Wesley Powell Auditorium of the Cosmos Club here in D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on the PSW Science YouTube channel. We will begin with a few announcements, a reading of the minutes of the 2,397th meeting on the proposed Dragonfly mission to Titan. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Before we get going, where are we here? Hello? All right, that's who we are. That's what we're doing. Please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization, in cooperation with the American Public University, and a generous anonymous donor. Thank you. I am pleased to announce that the following new members have been elected to the Society. Bryce Eldridge, a technology consultant interested broadly in the sciences, who learned about PSW through a newspaper article. Colin Alberts, an attorney involved in radio frequency spectrum management, interested generally in physics, astronomy, biology, especially genomics, and information theory, who comes to PSW through his friend and member Erica Kane. Iva Alexova, a software developer with simplicity, generally interested in computer science, neurosciences, genomics, and biotechnology, who comes to PSW through the PSW Meetup group. Mirjana Puig, a DSP engineer with QRC Technologies, particularly interested in satellite communications, RF spectrum analysis, digital signal processing, and software-defined radio, who learned of PSW at the National Capital Astronomers at the UMD Observatory Open House. And tonight's speaker, Charles Norton, whose background and interests will, to some extent, be clear to you from tonight's proceedings. Please join me in welcoming all to membership. All new members receive a signed copy of Volume 1 of the PSW Bulletin. To obtain your copy, if you're here tonight and you're a new member and you haven't yet received a copy, please see me after the lecture. Recording Secretary James Hewin will now read the minutes of the 2,397th meeting and the lecture by Zibby Turtle on the proposed Dragonfly mission to Titan, delivered here at the Cosmos Club on October 5th, 2018. James.
Thank you, Larry. On October 5th, 2018, President Larry Milstein called the 2,397th meeting of the Society to order at 8 p.m. in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live-streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Zibby Turtle, planetary scientist at the Johns Hopkins University Applied Physics Laboratory. Her lecture was titled Dragonfly, Exploring Titan by Rotorcraft. The largest of Saturn's 62 moons, Titan has an opaque, orange, methane-rich atmosphere that obscures its surface. Because methane breaks down and escapes, there must be a source on the moon to replenish it, such that scientists hypothesized the existence of a global ocean of methane on Titan's surface. The Hubble Space Telescope first saw through Titan's atmosphere and revealed surface features in 1995. Subsequent telescopic observation confirmed the Titan's surface is not uniformly smooth. Turtle said Titan's bedrock composition is water ice, covering a deep liquid water ocean that may interact with organic elements on the moon's surface. In 1997, NASA and the European Space Agency launched the Cassini-Huygens mission to Saturn, which arrived in July 2004. 6 months later, the Huygens probe descended through Titan's atmosphere and landed on its surface. And for the next 13 years, the Cassini orbiter made 126 close Titan flybys. Cassini-Huygens revealed the details of Titan's surface. For example, it has a surface temperature of 94 Kelvin, a water ice surface, and surface dunes comprised of organic compounds. In sum, Turtle said Titan has the key ingredients known to be necessary for life: energy in the form of sunlight, abundant carbon and complex organics, and solvents, specifically liquid water and methane. Turtle said that scientists now know Titan is sufficiently Earth-like to be useful in answering fundamental questions such as, what makes a planet or moon habitable? And what chemical processes led to the development of life? From the Cassini-Huygens observations, scientists believe they know specifically where to look on Titan for answers to these questions. The challenge is to get a capable instrument suite to multiple high-priority sites on Titan to sample materials and to measure compositions. Mobility, Turtle said, is key. Because Titan's atmosphere is 4 times denser than Earth's, and its gravity is 1/7 of that on Earth, Turtle said that flight would be a remarkably efficient means of surface transportation. Turtle's team therefore proposes to explore Titan with Dragonfly, a dual quadcopter designed to land, make measurements, and fly and scout to travel to new locations. Dragonfly will be battery-powered, recharged by an MMRTG between flights, the same power source used by the Mars Science Laboratory on NASA's Curiosity rover. Dragonfly's science objectives are to analyze the chemical components and processes that produce biologically relevant compounds, take atmospheric measurements, and search for chemical evidence of water-based or hydrocarbon-based life. To do so, Dragonfly will carry a mass spectrometer, a gamma ray and neutron spectrometer, meteorology, seismic, and geophysical sensors, and a camera suite. Turtle described those instruments and the specific experiments they will carry out. If accepted, Dragonfly plans to launch in 2025, arrive at Titan in 2034, and land in Titan's equatorial interdunes to conduct 2 years of surface exploration. NASA is still reviewing the Dragonfly proposal and is currently scheduled to make a decision on it in summer 2019. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the Society. At 9:40 p.m., President Milstein adjourned the 2,397th meeting of the Society to the social hour. Temperature, 17 degrees C. Weather, mostly cloudy. Attendance in the Powell Auditorium, 82, and viewing through the live stream on the PSW Science YouTube channel, 28. Respectfully submitted, James Heelan.
Thank you, James. Are there any comments, corrections, questions on the minutes? Hearing none, I will entertain a motion by a member to approve the minutes as read. A second? Okay, we have lots of seconds, so the minutes are approved as read and will be posted without change to the website in due course, perhaps accompanied by music. And we'll now turn to tonight's lecture on SmallSats, and it's my pleasure to introduce tonight's speaker, Charles Norton. Charles is the Special Advisor for Small Spacecraft Missions at NASA. He's responsible for advising NASA on cross-agency strategies for small satellite science, exploration, and technology. Previously, he was Program Manager Associate at the JPL, developing technologies for mission flight validation for NASA's Earth Science Technology Office. His research is focused on high-performance computational science in the Earth and space sciences, particularly for flight validation of new instruments and information systems technologies on small spacecraft. He is an author of numerous technical journal articles and book chapters. Among other awards, he received the JPL Lou Allen Award, the Voyager Award, and the NASA Exceptional Service Medal. Charles earned a BSE in Electrical Engineering and Computer Science at Princeton University and an MS and PhD in Computer Science at Rensselaer Polytechnic Institute. Please hold questions for the question and answer period at the end of the lecture. And join me in welcoming Charles to the podium.
Oh, thank you very much, Larry, for that kind introduction. Thank you very much. It's a great pleasure for me to be here to meet with all of you and to talk to you about a not so unfamiliar to me, but perhaps new to you, revolution in space science related to small satellites. I am very pleased to have a number of colleagues here that I have worked with, and I am also very pleased and honored to be welcomed as a new member of the Philosophical Society of Washington. So I would actually like to begin by talking to you about a model that I brought this evening of a small spacecraft that I brought from the Earth Science Technology Office. And it actually has a name. It's called HARP, and that stands for Hyperangular Rainbow Polarimeter. And it turns out this is an actual model, realistic, of a spacecraft that we hope to launch next month from the International Space Station. And what it is it's a mission that will measure Earth's cloud and aerosol properties. And what's amazing about these CubeSats beyond their size, this one is roughly 10 centimeters by 10 centimeters by 30 centimeters, is that spacecraft of this kind actually contain all of the major features and components of much larger systems. In fact, if we take a closer look here, you can see communication antennas, deployable solar panels, there's actually well, I should point it out to you here. Right over here, you can actually see a fisheye lens, which leads to imaging electronics within the system. It has an attitude determination and control system to help ensure that the spacecraft will operate in a stable way and that we can point it in the way that we need to. And it also includes GPS antennas and many other features, including flight software. So it's quite amazing how maturation of technologies have allowed large spacecraft to be shrunk down to this size and still perform effective science. But before going on and talking with CubeSats, I'd actually like to go back through some history and talk to you a little bit about what we've been able to achieve in other areas. But within NASA, of course, the Science Mission Directorate has a number of focus areas that are integrated to create great science. We perform research in solar system exploration, in heliophysics, astrophysics, and earth science, and we do partner with other organizations through the Joint Agency Satellite Division, for example, with NOAA. And it turns out, as you can imagine, that there's a very rich diversity of satellite missions that NASA has flown over the years, which have enabled great science. You can see here many Earth science missions, missions that have explored Mars and the outer planets, a number of very important missions in astrophysics and also in heliophysics. And this operating and future fleet really represents a large percentage of how we achieve most of our great science. And it's of particular interest for this talk, I think, to review the history of great discoveries that have been made with these large missions. Because even as we look to the role that small satellites and CubeSats can perform, there's a legacy that we want to continue to preserve. And we want to ensure that these small missions can also actually perform great science. So in fact, as we go through and review some of the work that has been done in the past, you may notice some possible connections to the capabilities that we will soon be demonstrating on these small missions. So it's wonderful to begin with Cassini. As you know, Cassini is really one of the most serenely beautiful planets in our solar system, and it recently completed its grand finale. But what we've learned so much from the mission, and probably most recently and most importantly, is that it really represents a regime of our solar system which really has the fundamental building blocks of life. In fact, as you know, on Enceladus, geysers have been discovered. There are roughly 100 geysers that have been found, particularly within this area known as the Tiger Stripe area. And it's been shown that these geysers have been able to actually eject water into the local atmosphere. And of course, Cassini couldn't actually dive into those particular geysers, but one might think what the possibility could be for future scientific discovery if in fact we had small spacecraft that traveled along with the mission that could be used in that way to do a deeper investigation into these regions. In fact, looking at Cassini and the recent work that has been done associated with its end of mission, it's actually been proposed that perhaps some of the greatest science from this wonderful mission might actually have been achieved and is still being understood as a result of measurements that were made through this highly risky maneuver of actually flying Cassini through its rings. Indeed, many of the things that have been discovered include ring material that has actually been discovered as a result of the mission, containing very complex organics that were not known to exist. And indeed, those organics are falling into Saturn's atmosphere. There have been new electric currents that have been discovered between Saturn and various rings. And that, in fact, in combination with other discoveries associated with a new understanding of the magnetic field of the planet, may help us actually unravel current mysteries associated with the rotational speed of Saturn itself. And in fact, unbeknownst to us before this final maneuver to end Cassini, we have since discovered this new radiation belt, which had not existed. So it's also very, helpful to ponder, what more we could learn if we had additional satellites where we could take greater risk, which could make these types of discoveries in that unexplored region until now between the planet itself and Cassini's rings. In fact, we have some of the highest resolution cloud measurements that were made as a result of the mission activities. And of course, as you know, it was necessary to end Cassini's wonderful legacy by sending it into the atmosphere because of the potential for organics and other fundamental building blocks of life that have been found at Titan as well as within Enceladus. So we would not want to risk the spacecraft actually falling into those moons. But there have been other great discoveries that have been made with large strategic missions. The Juno mission, which is currently orbiting Jupiter, has detected at the South Pole these turbulent cyclone regions, which are not only just beautiful to look at, but extremely scientifically interesting to observe. And the Juno mission is carrying one of many special instruments. One happens to be a microwave radiometer, which allows us to understand properties of Juno's atmosphere as well as measurements of aspects of its interior. And again, when we think forward about what we could do potentially with small satellites, one might imagine carrying missions that have many multiple radiometers so we can get near real-time 3D continuity measurements of this kind to explore and understand even further our depth of understanding through these simultaneous measurements. And of course, we all know the Hubble Space Telescope. Probably from a social media point of view and popularity point of view, there may be no mission that has received more attention that NASA has developed. And what we're looking at here is actually known as the UFO galaxy, simply because of the edge-on spiral nature of the galaxy that has been discovered. But of course, missions of these kind have not only advanced our knowledge, but have also had a very deep personal impact for the scientists that were fortunate enough to participate in them. But they don't happen often. So one might think, what could be the role that small satellites could play where individuals can launch missions much more frequently and to be able to make measurements of this kind much more rapidly. And indeed, Kepler, which you're, I'm sure, also familiar with, here is a image which is a very relatively small field of view of Kepler, but it's an 8 billion-year-old cluster looking at roughly 13,000 light years from Earth of the cluster of stars here. And Kepler, of course, is a mission which is trying to look for transiting exoplanets in the habitable zone to again help us understand the potential for life in these regions. But again, one might even think about, is there a role that small missions could have in exoplanet hunting? And while a mission like this will look at a relatively large field of view, could we in fact conceive of missions that could be dedicated to particular stars and having a constellation of them to help us get a even deeper view to understand the properties of these exoplanets? And of course, a mission like this uses a method known as the transit method, where once a planet passes in front of the star, changes in its dimness, the velocity of the transit, as well as other properties such as the temperature of the star itself, can help us understand many of the conditions that might help us look for possibility of the signs of life in these habitable regions. And indeed, there have been many great missions in Earth science over the years. This is an animation from Aura, and it's showing how we can quantify fire emissions from methane. But again, the ability to make these types of measurements and to have a greater understanding of our home planet is of great interest to those that are building small satellites. Again, Aura is a large strategic mission. It orbits the Earth with other large missions, but there's a greater interest and potential in having near real-time, constant, global coverage that could be enabled by constellations of small missions. And not only NASA, but commercial industry is also exploring these possibilities as well. And even turning to heliophysics, SOHO, of course, was a mission that gave us some of our early and highest resolution measurements of the sun at the time, and it sort of revolutionized, or definitely revolutionized, our understanding of coronal mass ejection events. And these types of events have serious impacts, not only as we look towards work in the human flight program, but also with maintaining the continuity of satellites and other electronics in low Earth orbit. But again, it's a point measurement in some sense, and there are great scientific discoveries that might actually be made through having multi-point measurements of the solar wind and other solar effects to help us improve our models for prediction of such effects. But even within the past, NASA is very interested in exploring more work using large strategic missions, and the future actually remains quite bright. In fact, the Parker Solar Probe launched not that long ago, and it's actually referred to as a mission to touch the sun. It will be a mission which is actually going to fly closer to the sun than any other mission. It will also be the fastest human-made object that has flown in the universe. But again, fundamental properties associated with our understanding of stars will be explored by this mission. And these large strategic missions play an important role in growing our understanding in these ways. Again, in the future, the very near future, there's a mission called NISAR, which is a joint effort between NASA and India to develop a radar mission to help us understand geophysical properties of the Earth and solid Earth dynamics. In fact, measurements from NISAR will help us understand coverage in space and time associated with ice mass change and many other properties. And missions of these nature are also collecting lots of data. NISAR will take about 85 terabytes of data daily to understand these complex processes. And sometimes you actually just need a large mission for certain measurements if they are going to be high data rate measurements. But again, you know, the question is, for a mission that's of this size and magnitude, is there the possibility of even developing smaller satellite radars which can play fixed roles in understanding other properties of Earth science applicable to missions of that size? And indeed, Europa Clipper is a mission which is in development now, and it will make use of the Space Launch System, the SLS. And this launch capability that NASA is developing will allow for direct inject of these large missions into particular regions. So we would not have to rely on gravitational assists around other bodies, and it could reduce the time for a mission of this nature to get to Europa by 50% as opposed to other mechanisms. But of course, Europa Clipper is an important mission to help us understand the ocean world's issue, which is, are there regions that are suitable for life in possibly hazardous zones, such as the Jupiter radiation environment, but where we know there's frozen water ice, and where due to planetary heating, there is the potential that there may be life below that ice. And a mission like Europa Clipper and the instruments that we'll carry will help us understand these things. So these are all wonderful achievements, but there's a challenge. these large missions require large resources, and those resources take many different forms. If we look at a mission like Cassini, you need a lot of people, both nationally and internationally, to develop and conceive and launch and operate and do the science data understanding of these types of missions. And, you know, they don't come along very often. And these missions are often competed. So there will be some lucky PI that is fortunate enough to win an award to develop a mission like this from conception to implementation, and that could take many years. In fact, going back to the NISAR mission back in the late 90s, I was participating in a study group looking at the need and possibility of developing a large L-band radar mission for solid Earth geophysics. And now in 2018, you know, we are well into the implementation. But I would have to share that looking at the new community of scientists who are coming up out of graduate school and other areas, there's a little less patience now than there has been in those days. And, you know, people want the opportunity to conceive of their science missions, to develop them, to own the entire process, to work in tight, small teams that can work quickly, and to advance our knowledge and capability rapidly. And while, again, there are needs for the large strategic missions to be developed in the way they can be, and that will continue, there is a new generation of scientists and engineers that want to experience scientific discovery on a much more rapid scale. And that actually is a capability that small satellites can enable. But in addition to people and time, there is dollars and money, and large strategic missions are expensive. This is a chart which is showing the expenditures from NASA for science missions in FY15 dollars from 1969 to 2026. So you can see in the early days, we had a fast and furious period with Viking and Voyager, where a lot of resources were dedicated to those missions over a very short period of time. And you can see many other missions here which have been developed over time. The shuttle launches, Earth science missions such as Terra and Aqua, the Mars Science Lander, Mars Observer, the Spitzer Space Telescope, which as well have been developed over a period of time and have cost, you know, in the millions of dollars. In fact, when you look at this chart, the most expensive mission by dollars over time has actually been the Hubble Space Telescope. And this information does include servicing, but it doesn't include the operations costs. So there have been actually other expenditures there. But has that been worth it? Yes, of course it has been worth it. But when we look at the potential of at least realizing that we need to explore the ability to do more with less, it does provide an avenue to try to assess, you know, what is the role that small satellites could have to develop missions rapidly, sometimes as short as a 3-year time scale from conception to launch, and also to develop missions in a way that are cost effective given their focused science objectives. And will small missions actually be able to achieve all the objectives of large missions? No, probably not. But sometimes 80% of the science at 20% of the cost can be good in some ways. But another aspect I think that small missions can provide in this context is the ability to replace them if necessary over a short period of time. So if you have missions that are quick to develop, that are relatively affordable, and can actually adopt and use the newest and latest technology, it can provide a mechanism to get very strong results in a very efficient way. And in fact, it's really these technology maturation activities that are enabling these breakthroughs in our scientific discovery. As you will see here, we have an area of small satellite constellations which form what's known as a disruptive innovation. And that's an innovation which may come from an unexpected source. In fact, much of the CubeSat development, you will soon learn, has not come out of a focused government program, but in fact from activities that have been developed within universities. And sometimes these disruptive innovations may be less capable in the beginning, but what can happen is by the nature of being able to move quickly, they can actually mature rapidly over time and become an important part of scientific exploration. In fact, if we look, for example, at the history of computing, when I first started working on computers, they were either large mainframes and even in some cases large desktop devices. And the laptops of the time were actually quite clunky and inefficient. It didn't work very well, but they had the advantage that they were portable. And that actually led them to come into greater use. And as time continued, the capabilities of these laptops grew. And now it's much more prevalent to have people operating with laptops usually as their computing device than larger desktop computers. So it was disruptive in that sense. Much like the cell phone cameras on our phones have disrupted many of the old single lens reflex cameras. But it's this push to understand what the impact of a technological change can have versus the rate and type of technology that has really driven the revolution in small satellites. You will still have breakthrough innovations that may not be based on small platforms, as well as game-changing innovations as well. But the key thing is that you could bring the newest technology and have the biggest impact with these systems if you can evaluate and determine what they are particularly useful for, if you are willing to put the time and effort into maturing the technology. So one area as an example where technological innovation has been really quite astounding has been in the area of hyperspectral imaging. So on the left here, this is an airborne hyperspectral imager called Avarice, which had its first flight in 1986. And you can see by the gentleman standing next to it, it's a quite large and massive system. But it turns out through changes in electronics and detector design and optics and other areas, by 2012, in fact, NASA's Earth Science Technology Office was able to make an investment to dramatically reduce the size of this particular instrument, yet to provide a equivalent capability for hyperspectral imaging. And in fact, on the right here is the Moon Mineralogy Mapper, which actually had its first flight in 2008, and it flew on an Indian mission to the moon. And it actually helped perform global maps of the composition of the moon, which you see in the background here. And in fact, it really helped the world discover that the moon is just not a gray body of no interest. There are actually very complex processes happening on the moon. And in fact, detection of water was enabled through this system. And these types of observations have impacts not just for science, but also for in situ resource utilization and the human program. And it's this ability to leverage and develop miniaturization of electronic components, which in fact was an important part of enabling the CubeSat revolution. And that revolution really started with these two gentlemen here. So on the left is Jordi Puig-Suari of Cal Poly San Luis Obispo, and in the middle was Bob Twiggs of Stanford University. And they were both educators that were very much interested in trying to bring space to a level where students can get involved and get the hands-on experience of conceiving, developing, and flying flight missions. And they had proposed two important things. One is a standard through which satellites could be developed by students, which could be universally applicable and tied to another important device, which is called a dispenser. And I'll show you an example of what these dispensers look like soon. In fact, Over here on the right is one of these dispensers called a P-pod. And what it does is it allows a very standard and safe do-no-harm mechanism for putting CubeSats on launch vehicles. So you can imagine that there may be some concern where if you have a billion-dollar flight mission on a rocket, that if you also agreed in a rideshare sense to carry some other spacecraft that may be developed by students as a training exercise, that if something went wrong, there could be a serious problem with that investment. But one of the advantages of what Jordy and Bob did was they created standards and mechanisms to protect the main payloads of these launch vehicles, and that allowed for more missions to get into space through the student community. And the benefits of this approach have been quickly observed and adopted by others. Indeed, within NASA now, I'm very proud to show a chart which shows the actual extent of small satellite and CubeSat work that's going on with the agency at this moment. And as you can see, there are many missions here that have been developed for Earth observation, and also many here that have been developed for heliophysics observations. And the locations on these charts show the nature of the observations, not necessarily where the spacecraft are orbiting. We have some new work going on in astrophysics, which is very exciting because most people would think the only way to do good astrophysics is to have a very large aperture and very cold detectors. But the platform is generating new curiosity within the scientific community and innovative methods of exploring scientific regimes that had not really been thought of prior to the development of this platform. And it turns out there's a very rich set of activities that can be done with CubeSats in astrophysics that are very exciting. And additionally, there's interest in developing CubeSats for planetary science and also for other planetary activities. CubeSats going to investigate asteroids, doing flybys of Mars, and even trying to understand issues associated with planetary formation. So not only has there been a revitalization of spacecraft development associated with this platform, but also a revitalization in thinking associated with what can be achieved scientifically. So if we want to think about what a CubeSat is, and we touched on this a little bit earlier, as mentioned, the basic definition is basically a 10-centimeter cube. This particular CubeSat has an antenna here, which is currently tied down by fishing line. In fact, there's a resistor that gets tied to the fishing line and breaks it, and that allows the antenna to deploy. And most people are surprised to find out that these antennas are basically just tape measurers you can get from Home Depot. But in fact, they work very, very well as spacecraft antennas in certain regimes. And they do carry smaller instruments. This CubeSat has a very small camera here, and it's called a 1U because it's a one-unit CubeSat, 10 centimeters on the side. This is a 3U CubeSat, just like the model I showed you earlier, because it's essentially three CubeSats stacked tall as one specific device. And again, you can see your favorite Stanley tape measure antenna being tied down there. And you could be very creative regarding the types of instruments and measurements that you can make with these systems. But in addition to other basics associated with CubeSats, as I mentioned, they have to be integrated to launch vehicles. So this is a large mission called the MPOS Preparatory Mission, which is taking up a large part of the fairing of the rocket. And down here is one of those P-pod dispensers I mentioned, which has 3 little CubeSats inside of it. And what happens is that when the primary payload is released, there will be an orbital plane change, and then the mission commanders will release the small satellites into space. And here again, you can see the P-pod dispenser, which really acts like a PEZ dispenser. It's simply a container with a lid and a spring inside. And when you open the lid, the spring pushes the satellite out, and off you go. And it turns out, there are very strict requirements that are associated with putting these dispensers onto launch vehicles. They have to be completely off on ascent, so they do not interfere in a radio frequency sense with the primary payload. But as long as you meet a full set of requirements associated with the mission, you can literally do almost any type of experiment that you can conceive of. And there's also a great interest in carrying other types of small satellites together as grouped payloads on large missions. So these rings here are called ESPA rings, and they can carry small satellites that can go anywhere up to 180 to maybe 350 kilograms. This small satellite that I have here that I've shown to you is only about 5 kilograms roughly. But again, if you can think of the cost advantage of deploying many satellites simultaneously, this is certainly a direction that the community is moving in. And one of the important things to realize about these CubeSats, again, is that they are full flight spacecraft. There's often very little that you can distinguish in a substantive sense between what a large, bus-sized spacecraft may be carrying internally, as well as these small satellites. This is a very special small satellite called RainCube, which is a precipitation radar, and it has a deployable mesh antenna that is used as part of sending pulses and receiving them to measure precipitation. And inside, you can see they very carefully packed all the electronics that are needed to operate the system and to control it from the ground. There are solar panels that provide solar power. There are batteries, again, an attitude determination system and other electronics and flight software. The canister here that deploys the antenna. So it's a very sophisticated system. And all of these subsystems that I've mentioned here, such as the command and data handling system, the radios, the thermal control system, the GPS and the antennas, have all been miniaturized and can be compacted and used in these systems. And it's quite amazing what you can achieve, and I look forward to talking about that in just a moment. But again, people often ask, how do you get to space? Well, it turns out that NASA has a program called the CubeSat Launch Initiative that allows universities and nonprofit organizations to submit proposals and get to space at no cost. And that's been a tremendous force multiplier in the ability of engaging students and other organizations, because the cost of launch is often prohibitive. But through a program of this nature, many CubeSats have been selected. There have been many organizations that participate, including universities, and they fly on a variety of launch vehicles. Some of them are not even NASA procured. In some cases, we even work with other government agencies, because many see the benefits of this system to provide access to space. And in fact, this is an image from one of the very first launches that I was involved in with delivering payloads. And again, there's nothing quite as exciting as actually being to a launch and actually watching your system go to space. And through the ability of developing these small CubeSat missions, this is happening on a very regular cycle, and there are more people that can be involved in that. And it's really opening up the ability to just expand the rate of discovery, which is really one of the great goals that a mission of this kind can provide. Indeed, I showed you the P-pods. They often are put at the back end of a launch vehicle. In this case would be a Centaur, and they can be deployed safely into space. And once they're deployed, they will turn on after a period of time, because again, we want to ensure that there is no radio interference with the system and other spacecraft. But then they can be stabilized, they can look for the sun, and they can start phoning home by communicating with ground stations on Earth. And what's particularly interesting is that many of these satellites operate in the ham radio frequencies. So there are amateur radio observers that can actually listen in and decode data from these satellites that are in space. And many of them are very excited to track when launches will occur, and they want to be the first ones in the world to actually pick up the initial beacons and confirm to the world that someone's spacecraft is alive. So it's actually providing a mechanism to engage the broader international community in missions that are flown. But another way to get missions deployed is from the International Space Station, which in and of itself is a great scientific observatory. But we do use the International Space Station often to deploy CubeSats. It has a great advantage that it's a much gentler ride to space than taking the method that I showed before, being at the back end of a launch vehicle where there was once a fuel canister and you're right next to the thruster. It's a very rocky road, but we do a lot of testing to ensure that we can survive that low vibration. But the ride to the space station is very comfortable. You get suited up in nice airbags and a very comfortable, warm, safe environment, which is pressurized, and you get white glove handling by the astronauts. So it's actually a very, very nice way to get to space, particularly if you have very sensitive instruments. But what you can see here is actually deployment of CubeSats, and this is real imagery. These were two that launched not long ago. One is called HaloSat, and the one behind it is the RainCube mission that I mentioned. And you can see at this point, they're flying in a very nice configuration, but at some point they will start to turn on their attitude control systems, try to orient themselves to the sun. They will deploy their solar panels and then start their communication phoning home to be in touch with Earth. And one of the great things about deploying from the International Space Station is that we can limit the amount of CubeSats that remain on orbit as future debris. From the space station at roughly 500 kilometers, we could actually expect that these systems will deploy in roughly a year to, will degrade into the Earth's atmosphere and burn up roughly a year or year and a half into their lifetime. So it's a great opportunity that we can use to test new technologies and to explore how we could make Earth science measurements in an effective way. And it is true that a lot of effort goes into developing these systems, and there's always great hope when someone actually delivers and is excited to look forward to their mission getting on orbit and collecting their data. But it is also a reality that sometimes failures do occur. This was a launch failure that happened at the Wallops Flight Facility some years ago. And this was a mission that did not contain people. It was a unmanned mission to bring cargo up to the space station. And even though it can be disappointing when these things happen, the benefit and one of the great principles of these CubeSats is that you can develop them rapidly and fly again. In fact, you might be surprised to learn that even though this looks and was a very serious anomaly, there were actually CubeSats that survived the explosion and were reflown just a few months later with very little modification needed. Of course, there were many other systems that were completely lost, but in that case, industry that was flying these systems could rapidly develop them and get on the next available launch. And it's hard to conceive that for a much larger strategic mission that you could recover that quickly. And it's really one of the benefits that these systems can provide. But failures also do happen on orbit once you've deployed. This is a mission called Murata, which was making microwave radiometer measurements that was going to determine for the first time that you could use a combination of GPS radio occultation and your microwave measurement to do on-orbit calibration of the microwave radiometer instrument. And the hope here was that we would be able to demonstrate that technology and fly it on future spacecraft, because for the most part, that calibration work has to be done on the ground. But we launched the mission, got initial contact with it, and things seemed to be going well, but then we started to notice anomalies and power issues. And eventually, unfortunately, we lost the mission due to an on-orbit power failure. But again, this team has since gone on to develop other missions only 2 years later and have been able to demonstrate wonderful results as a result of that. But what I would like to do now is to highlight for you what we are actually doing with small satellite missions in NASA. And in fact, we have the Marco missions, which are 2 6-unit CubeSats that are currently on their way to Mars, and they will actually be rendezvousing to form what's known as a bent pipe relay to capture the entry, descent, and landing signal from the InSight lander and relay it back to Earth. But it's really a important technology demonstration because it's the first time that CubeSats have left low Earth orbit, and they're advancing many technologies associated with going to deep space. So in fact, here is the InSight mission, which is actually launched from the West Coast. It was the first time we had a mission of this kind launched from the West Coast. And it, in fact, also carried the 2 Marco CubeSats. Again, you can see them dispensing here from their dispensers, 1 on each side. The spacecraft will make orbital maneuvers to ensure that they can fly in a way that they will not become conjoined or possibly collide with each other or the InSight lander. And what you can see here are some of the solar panels of the system. They will deploy and provide additional energy to the battery systems. On the back here, you can see various other radio communication systems that are used, because these are also the first satellites that have to communicate with NASA's Deep Space Network to talk to Earth. So it was also a very important technology demonstration to show that CubeSats can communicate in that way. And in fact, because they are free flyers flying along with InSight, they have to provide their own navigation and trajectory correction maneuver capabilities. And there you just saw deploy another important new technology, which is a high-gain reflect array antenna. It's the first time a reflect array antenna has flown in space. You saw those circular-looking patterns. Actually, it's a flat antenna, as you can see from the deployment, but the pattern of those radiating elements actually makes it look like a parabolic antenna. So as InSight is transmitting, the Marcos will collect the signal and retransmit it to Earth, because InSight will be in a position where it will not have a direct line-to-sight communication to Earth during the entry, descent, and landing sequence. It will actually communicate data up to the Mars Reconnaissance Orbiter, and that will be forwarded later to Earth. So the Marco missions, in fact, work on a non-interference basis with the mission, but it will give us the opportunity to get that near real-time response to understand the health of the mission and to demonstrate that CubeSats can operate well in deep space. And in fact, this is a very important image. Not long after deployment, the team wanted to verify that all the deployable elements worked properly, and they were able to actually capture an image of the Earth as well as the Moon from their cameras on the spacecraft. So this is a very unique and important image showing how deep space CubeSats can actually make these types of observations. And there are many other exciting things that are in development. There's a mission called Lunar Flashlight, which will use lasers to support human exploration by looking for water, ice, and other volatiles that will be necessary for exploring the Moon. And as I mentioned, this is an area which is rich with student involvement. So this is Luna H-map, which is a polar hydrogen mapper, which will actually look for hidden hydrogen in the permanently shadowed craters of the moon. And in fact, we've also made solar measurements with CubeSats. In fact, this mission called MINX, which is the Miniature X-ray Solar Spectrometer, was the first science CubeSat mission that was funded. And it is making measurements of photon energy associated with coronal mass ejections. And this mission has made very important scientific measurements from a regime of Earth's atmosphere where we had, prior to this mission, no understanding of the effect of coronal mass ejections in that region. So it's made a number of very important discoveries in that way. This is another mission called the IceCube mission. It's an ice cloud imaging radiometer. It's a spacecraft spinner, and what it is doing is measuring cloud ice particles. Prior to this mission, there was no global map produced of ice particles in clouds at the 883 gigahertz radiance regime. And again, even though you can see that the data looks coarse, as I mentioned earlier, with these disruptive innovations, in the beginning we may not have the highest quality measurement, but this is actually a measurement which is unique and has not been seen before, and it was made by a CubeSat mission. We also have flown and are developing constellation missions using small satellites that are larger than CubeSats. So this is a mission called Cygnus, which in fact uses a technique called GPS reflectometry, where it is measuring the reflected GPS signal to help us understand improvements in modeling and measurements of the intensity of hurricanes. But one of the interesting benefits of missions of these kind is that they can also provide secondary important measurements. And one important measurement that Cygnus has demonstrated it could do is also make soil moisture measurements that are comparable to a larger mission called SMAP, which is a soil moisture active-passive mission. It uses a different technique by looking at the change in the signal-to-noise ratio coming from the instruments on Cygnus, but it just shows a mechanism where we could actually go ahead and make equivalent measurements using new techniques. We recently launched a mission called TEMPEST-D, which is very exciting. It's another radiometer mission, and it's an area where, again, technology advancements have shrunk down the sizes of these instruments and can enable new things. And TEMPEST-D, in fact, was able to observe Hurricane Florence, which is right here. And using the radiometer, it was able to peer into the hurricane to give us information about its structure. And this actual instrument carries 5 different types of radiometers, so we can look at various levels of the storm structure. And this, in fact, here is what the 6U spacecraft looks like. And it has here a small rotating element which performs the scanning. And you could imagine flying a constellation of these systems to get global, near real-time coverage of atmospheric dynamics. I talked a little bit about the RainCube mission. It's actually the first radar mission on a CubeSat. It was specifically designed to look at specifically designed to look at precipitation, so it's a precipitation radar. Here you can see the flight path of the mission here past Japan, and it was able to make measurements of Typhoon Trami peering into the eye of the storm. So here you can see the radar reflectivity measurements, measuring the stratiform rain up to about 10 kilometers in altitude down to the ocean surface, as well as the mid-latitude frontal system. And again, there were many who thought that radars must be big, high-power instruments, and they could never be reduced to the size of flying on a CubeSat mission. But that's been demonstrated in this particular Ka-band regime. And again, one can think of what you can do with deploying a constellation of these systems to enable near real-time global coverage. But what's also interesting with these constellation missions is how you could actually combine results. And we were fortunate to fly both RainCube and the TEMPEST-D mission off the ISS in the same flight. So they are actually following each other in an orbital trajectory right now. And what it has allowed is for us to start to look at getting at new types of measurements through multiple sensors. And in fact, what you can see here is really a first-of-a-kind measurement where we've been able to combine the radar vertical structure along with the layered structure from the radiometer from these two missions. So it's giving us an insight into actually the 3D structure of the tropical cyclone. And even though these measurements were made 5 minutes apart, so they're not exactly coincident, one could imagine the capability of deploying many systems of these kind that make many different measurements semi-simultaneously and that allow for one to get this type of 3D structure that heretofore we could not really measure using a single spacecraft alone. And again, you know, the benefit of these CubeSat systems is the ability to deploy them in large numbers. So there's a mission in development right now called Tropics, which will also look at precipitation structure and storm intensity by flying a constellation of them to make various measurements, to cover wide swath areas, to really revolutionize our understanding of these systems and to improve our models for forecasting, and as a result, human impacts. But even though these missions are focused on science and technology, you can have fun too. So this is a mission called Raven, which is actually a solar irradiance measurement mission. It's trying to understand the difference in the impact of ingoing and outgoing solar radiation on Earth. But it turns out this instrument needs to look at the sun to calibrate itself. So the principal investigator here worked with his team to actually observe the great solar eclipse of 2017. And while they were not actually in the path of full totality, they were able, through their instruments, to measure the impact in the reduction of solar flux, solar radiation flux, as a result of the active eclipse. So here you can see the sun and the amount of eclipse that occurred, and as the sun gets more and more obscured, the fraction of full solar radiance dips and then recovers. And it's you know, not only fun, but actually quite amazing that a measurement of this kind could be made from a CubeSat. But also people looking at the role that CubeSats could have in very new science, in particular with respect to gravitational wave detection. So the missions Fermi and LIGO worked together to look at gamma ray bursts. And it turns out that there was an event where Fermi was able to capture the gamma ray bursts, and at the same time, LIGO was actually able to capture the gravitational wave event. And that data could be simulated and combined in a way to give us new understanding of the event. So there are developers now building gamma ray detector CubeSats, which can be deployed in large mass, so that we could have a global outward-looking coverage of the universe to capture more of these events more rapidly. Right now, to some extent, if you have a single larger spacecraft, you have to sort of be in the right place at the right time to manage these types of interactions. But if on a CubeSat, you could capture the gamma ray bursts and then communicate with the LIGO observatories in a global sense, you can enrich the amount of science that can be achieved using these types of techniques. And again, we talked about astrophysics earlier, where most people believe you need large apertures to make significant measurements. Well, this is an exoplanet mission called Asteria, which was focused on actually advancing and proving new technologies using this technique of allowing measurements of the change in the light curve as the planet passes the sun. And this is the Asteria mission here, which demonstrated very high precision pointing as well as thermal stability to make a measurement of this kind, which one thought might only be achievable by missions such as Kepler. And in fact, up here is the actual light curve measurement that the CubeSat made using this technique, where you can see the dip as associated with a super Earth called Exo-planet 55 Cancri E, which is a known super Earth transit that Kepler discovered. So in fact, they were able to validate the quality of the measurement based on the prior one that was made. And it turns out now this mission is in an extended mission mode, where not only are they trying to test new technologies, but they're also working on performing new scientific observations that have not been made by other missions. Because it has the benefit that rather than looking at a global field of large potential candidates in the habitable zone, it could actually focus on an individual star, dedicate its time there, and use the properties of the change in the velocity of the planet as well as the light imaging to help us do these types of exoplanet measurements. But finally, I also want to talk about what people are looking at in the future. We haven't talked about large global CubeSats in the hundreds, or possibly in some cases people are looking at thousands to make new types of measurements. But it turns out in the area of low-frequency radio astronomy, people see a great opportunity to deploy CubeSats with radio antennas in very large numbers that can help us understand very many fundamental properties of the universe in radio quiet zones, such as beyond in the far side of the moon. And this is a mission concept which is looking at making those types of measurements. And in fact, there are international organizations that have recently launched missions of these kind to test the technique to show that low-frequency radio astronomy can be made using these CubeSats. And of course, as we talked earlier, understanding properties of the sun and their impacts on Earth are very important. And it turns out that most of these measurements are made in a regime where we can look directly at the sun to look at these coronal mass ejections. But there is an interest in deploying CubeSats of a very new type, which will go out to what's known as the Earth-Sun L5 point. And that's a region where you could make very unique measurements because you can actually see the rotation of the sun prior to the coronal mass ejection event. So here, of course, is the Earth. Measurements of this type are sometimes made at the L1 point in other areas where the coronal mass ejection is actually heading in the line of sight direction to Earth. But if you can come out to this halo orbit, you can actually observe the rotation of the sun and get more data to help understand the precursors to these coronal mass ejections to help try to improve the models that are used. And it turns out that you have to explore new technologies, such as the use of solar sails and new orbit transit techniques to get into the halo and linger in a way. But one of the benefits is that you can carry multiple instruments like heliophysics imagers and others on the individual CubeSats and dedicate them there to that mission. And there are new communication technologies that are being developed which will enable those high data rates to get that data back to Earth in a way to improve these predictions. So I would like to close by looking back a little bit. Of course, we recently celebrated the 60th anniversary of NASA. And as mentioned, originally coming from JPL before moving to NASA headquarters, I can't help but think about Explorer-1 and some of its relations to the small satellite work that was going on now and in the future. I mean, there were often small teams that develop and build their own ground stations, a small number of people that actually do the integration of the payload to the rocket, small launch vehicles that are developed and dedicated to small spacecraft missions, which is what Explorer-1 was. And also, you know, the fact that you can physically hold these systems in your hands. And in fact, you can even see the antennas here, not the Home Depot antennas I mentioned earlier, but nonetheless, not unlike the antennas in the model that we see here. And, you know, it's really quite nice to think about not only what Explorer-1 created and its legacy, but its impact even now when we think about what can be the role of small missions for advancing science. As you know, Explorer-1 helped us discover the Van Allen belts and was really our entry point into the world of space exploration for science. And, you know, as we look forward to the role that small satellites can provide, I'm fully convinced that missions of this type will open up a whole new world of discoveries that heretofore we could not even have conceived of before, that are uniquely enabled by these types of missions. So, you know, exploration is an important part of NASA's legacy and future. And, you know, I'm very pleased to play some role, along with the large number of collaborators and investigators and industry partners that I want to personally thank for working with us to enable these types of missions to allow us to go forth and do great work. So with that, I'm again very pleased and happy to spend this evening with you talking to you about small satellites. And it's been my great pleasure to be with you. So thank you very much.
So I think we have time for some questions. We have a procedure for questions. For those of you who don't know, there are people with microphones that have colored foam coverings, red, green, and what color back there? Maybe blue? But when you get a microphone, hold up your hand long enough for somebody to bring a microphone to you. When you get it, when I point to you, you stand, tell us your name, tell us if you're a member or you're not, and ask a question. Save the speeches for the social hour, please. Okay, question.
Yes, thank you. My name is Ms. Puig-Suari. I work in DC, and I am a member of the Philosophical Society of DC. And I had actually 3 questions, but they're very brief.
No, only one.
3 sections of my one question. First one is, you mentioned one of the systems is collecting 85 terabytes of data. So as you have more and more satellites, how do you manage your data and computational needs? Another question I had was, you know, around the orbit, there are more and more satellites that are going. How do you manage, even with the CubeSats, how do you manage keeping track of space trash?
Yeah.
And the last question, which was really fun actually, is, of course, you mentioned the private sector and, of course, working at the universities. So I also run a foundation, and we have a CubeSat program. What is the ratio between NASA, NOAA's CubeSat programs or CubeSats and the private sector, and how does that change in the future?
Okay, so let me see if I can remember all the questions. So maybe
data,
I'll work backwards.
Data, trash,
Okay, we'll talk about the data first.
Yeah.
Yes, so you know, it turns out that data issues are a challenge for small satellites. Most people tend to develop radios and submit licenses for those radios that really are very low data rate, maybe 9.5 kilobits per second, which would be equivalent to, you know, your modem from the, you know, mid-90s, and maybe in good circumstances up to 3 megabits per second. But it turns out there are not only new radios being developed, but new areas of the spectrum that people are exploring that allow for higher data rate systems. There are satellites now that can transmit at 500 megabits per second. I fully expect a gigabit per second to come soon. And I think that technology capability will continue, but it will also allow and require more ground infrastructure, particularly large dish antennas that can support that. But that work is ongoing. And your second question
Which was about trash floating in space, and how do you manage that with
Yes.
CubeSats being
So there
launched?
are requirements for CubeSats that they have to be the 25-year deorbit requirement, meaning that after their end of mission, you have to prove through analysis that the CubeSats will re-enter the Earth's atmosphere after 25 years. Many CubeSats right now do not carry propulsion or deorbit systems, but more of these missions are now looking towards including those capabilities to help take care of the space debris issue. And your third question
Yeah, the
was?
last one was the ratio between what NASA's doing, NOAA's doing, and the private sector, and how does that change in the future? So what can we expect
Yes.
from the private sector, and what support does NASA provide?
Yes, well, I would say that NASA and NOAA and the private sector sometimes have common objectives and sometimes have very different objectives. If I start with the private sector, there are companies that are very much interested in developing small satellites to support global telecom, and some companies want to launch 5,000 satellites within
Right.
the next few years. NOAA, of course, is very much interested in looking at what type of operational capabilities can be enabled through small missions. And there will be important requirements on reliability, because that will be very important to their operational needs. And within NASA, we're interested in revolutionary new science measurements and also flying technology. So in some cases, we're willing to take more risks to prove how these missions work. But the largest physical number of missions in the future will come from the private sector.
That's
Yes.
exciting to
Okay,
hear.
great.
Thank you for a wonderful presentation.
Oh, thank you very much.
We have Erica Kane up here, and then the fellow with the beard over there, who I think is a physicist at the end of this row. And Erica first. Can you get Erica Carl, can you give Erica the microphone? Okay, Erica.
Okay. Hi, Erica Kane. I'm a member of the Society. So one question I had was, you mentioned there was an interest in setting up networks of these satellites to cover the entire sky, for example, with the gamma rays. How many of those, for example, would you need to truly cover the entire sky? And I guess I also was wondering, with respect to the space trash issue, if you have a large number, which I assume is what would be needed, maybe I'm wrong, but even with a 25-year deorbit requirement, it seems to me you might get to a situation where that's going to be unmanageable at the time you have such a large network deployed. So how will you manage that?
Yeah, so for the Burst Cube mission, actually the investigators believe they don't need that many, certainly less than 30, probably more in the range of 15 or so. It really depends upon the particular orbit plane that you're in and the inclination. So in some cases, you don't need large physical numbers to get good sky coverage. And of course, they will be looking out, not in. Yeah, again, in terms of the orbital debris issue, it is a concern. I think, though, that the number of small spacecraft that are on orbit now is a very small percentage of the total amount of orbital debris, and much of the actual debris that is being tracked, and there was a question related to tracking before, is quite small. So as long as we're trying to be good stewards of the space environment by following the rules, that is something that can be managed. But as we continue to go forward, the real trick will be to ensure that investigators are following the rules and satisfy that 25-year deorbit requirement.
So if we get, our physicist.
My name is Scott Matthews. I'm not currently a member. My question is, would it make sense, or has any thought been given to the idea of taking a constellation of small satellites, which all have small apertures, whether it's optical or RF, that would somehow be distributed so that they would constitute a much larger aperture, sort of like a synthetic aperture?
Yes.
And would that provide some advantage over other techniques for studying deep space?
Yes, definitely. In fact, There are many answers to that question. There's a mission which is being developed right now that probably will launch next year, which is a reconfigurable space telescope that in fact has individual components which can be deployed and then reconfigured semi-autonomously to form a large aperture space telescope. And that's one example of what will happen in the near term. But there is great interest in looking at the possibility of doing either in-space assembly of connected small satellites or distributed small satellites with very good precision pointing and stability control to serve as a synthetic aperture for large observations. And those apertures don't necessarily need to be optical. They can be RF. But as long as you can meet the tolerances and the technology is getting there, you know, I fully expect that there will be synthetic imaging systems based on that capability. And the benefit is that there's a failure in one part of it, you can go ahead and replace that part and not necessarily lose the continuity of the entire mission. So it's a very exciting forward path.
Carl.
Carl Merrill, member of the Society. A number of years ago, I think Congress tasked NASA with monitoring for asteroids that might threaten the Earth. And there are gaps in our ability to see them, like coming from the other side, around from behind the sun.
Yes.
Is this participating in that monitoring, or is there thought given to that for this?
Yes, there has been thought given to that, and there are people that are working on mini satellites to support that. That is a region where, for the rate and quality of imaging, you do need a larger aperture, larger than, for example, the one that I'm showing on the 3U CubeSat here. But that is being investigated. With respect to objects that are hard to be seen but are transitory, there's also scientific interest in looking at other types of objects, such as mini-moons, where, again, a similar type of capability could be used. So it is of definite interest.
I think we have a few questions from our online viewers.
We do. The first one's from Patrick Shannon from Hyattsville, Maryland. There are some mechanics questions about CubeSats. What maneuvering capability do CubeSats have? What stabilizes the CubeSats? Can they change orbits? And what ground controls are necessary for CubeSats?
Yeah, that's a very good question. So these CubeSats actually have very sophisticated attitude determination and control systems. There's a 3U CubeSat that we're seeing here. These systems actually can be as small as half a unit, and they contain many components for those types of operations. They have 3-axis control reaction wheels, star trackers, they have actual telescopes with optics to reduce stray light contamination. In addition, there are other capabilities such as torquer rods that can be used when in the low Earth orbit environment to push against the Earth's magnetic field to support attitude determination and stabilization. So they have fully fledged attitude determination control mechanisms to support those types of operations.
Okay, there's one more question from Neil online. Given the recent news about our telescope fleet having failures, is it possible or feasible to have several CubeSats take over the pointing or gyroscopic reaction wheel tasks by attaching themselves as needed?
Oh, that's a very interesting question. Yes, it is true at the moment that Hubble does have an issue with its primary gyros as well as the backup gyro, and that is being investigated. But, you know, I think that's an area of exploration. There are those that are interested in proximity operations, and there have been proximity operation CubeSat missions flown where you could have the interaction between multiple spacecraft where they can conjoin to support each other and also separate for other reasons. And of course, you know, the size of your reaction wheels dictates the amount of motion you can impart on another object. So I don't foresee a CubeSat attaching itself to Hubble to address the issue of the gyro issue. But nonetheless, I think it's an excited area of exploration where the in-service spacecraft community would actually take a lead.
Bob?
I'm Bob Hershey. I'm a member. Could you tell us a little bit more about the CubeSats working with other spacecraft and doing things jointly?
Yes, so that's a good question because there's an interest in CubeSats supporting other large missions. So you could have examples where you may have CubeSats that will make precursor measurements in the atmospheric sciences, and then where those could be communicating with another large spacecraft to actually follow up with a more detailed measurement. It turns out actually in planetary science, there's a great interest in using CubeSats as secondaries to work with larger missions, not the least of which is at those distances, you will often need a larger mission to support the telecom back to Earth. But again, you know, even if you look at a non-CubeSat mission like Cassini, which carried the Huygens probe as a secondary to make those measurements of the liquid methane, you know, it's a much larger example. But there have been those that have thought of future planetary missions which could carry CubeSats and make those types of inner ring dynamic measurements where you do not want to risk the large spacecraft. And it's an example where you could have a collaborative nature to support advanced science while minimizing risk. So it's definitely a future path.
Any other questions? Tim?
Tim
And
Thomas,
then
a member of the
there's one back
society. I'm asking about transfer of this amazing technology down to terrestrial applications. I imagine that much of the miniaturization would be useful for UAVs, for cars, for lots of stuff in factories. Is that process ongoing and vigorous?
That's a good question too. I would say it's largely happened the other way around. Most of the CubeSat developers have relied on these commercial off-the-shelf or COTS parts that have come from other industries. In fact, some of these CubeSats actually carry auto-level quality parts in them because those parts are developed with high reliability because they have to work well in those automobile systems, and people want to adopt them into the CubeSats. So I would say it's largely happening the other way. Those technologies are being developed in other areas or coming to advance the capabilities of CubeSats. But again, there are some areas where there may be terrestrial applications that can benefit through CubeSat development. I would probably say in some areas such as very small, high precision microcontrollers and devices which are typically used in CubeSats in some ways that we've described regarding the attitude determination control could find their ways into other devices that need high stability. But it's really a healthy interaction between those two industries that support each other.
Woman in the orange scarf, and then the gentleman with the brown T-shirt and the white sleeves. But yes, you, orange scarf.
Good evening, everybody. For me, it's such a big honor.
Do you have a name?
My name is Norma.
And are you a
I'm
member?
from New York.
And are you a member?
No. My friend here, he invited me tonight for this beautiful meeting, which I'm very proud of Mr. Norton. And I learned so much about the deploy, something that I never heard before. I grew up with my family in Lara Science.
Do you have a question?
Yes. My question is this going to be reachable to all the students in college and in schools because they need this information?
Yes, actually, you may be surprised to learn that elementary school students have built and flown CubeSats, even high school students, but mainly university students. And it's a great platform for education, not only for technology, but I also think in understanding how to work and interact with teams and people.
Exactly.
I mean, many of these individuals actually have to present before review boards. I've had students sit and present to me, chairing their preliminary and critical design reviews, and it's a great experience for them to interact with those in the space community and to learn what it's like to go under the grilling for a mission that you're actually going to deliver to space to meet specific objectives. So the training and the educational aspects extend well beyond the technology capabilities that they will be learning about, but actually into their own personal life and future behaviors.
Amazing. And also, thank you, because besides I study astronomy in college, and also I'm astrologist. So all the information about the new planets and everything, all the discoveries, is going to help me so much.
Thank
Oh,
you.
thank you
Can
very
you give the
much.
microphone to the
Thank you.
gentleman right there? He's got his hand up, Lloyd, right in front of you. Lloyd, the guy who's got his hand up with the white sleeve. Thank you.
Hello, my name is Derek. I'm actually a cybersecurity engineer.
Are you a member?
I'm not a member as of yet. That's
Okay,
the key.
put the microphone closer to your mouth.
All right. I do
Thank you.
project too, so I wasn't going to give it too much. But yeah, one of my questions was surrounding one of the key advantages seems to be about the standardization of the CubeSat and the standard and having a form factor that's pretty consistent. And probably, I'm assuming the question, I was originally going to wonder if the materials were standardized as well, but you mentioned how sometimes they may come from other COTS parts, but like when it comes to deorbiting, and how do you ensure that its ability to burn up, its ability when
Yes.
you have all that variable material? And also, even I had a question around the community side of it, like, is it open source programming for the CubeSat that everybody has a standard that works on it, kind of?
Yeah, it's great to hear a software question because it's almost all about the hardware. But regarding your first question, yes, there are very strict requirements. In fact, all of these missions have to submit something called an ODAR, which is an orbital debris assessment report, where they look at all of the materials and the ability of them to actually burn up on the orbit. And in fact, we have had missions which have carried materials where we could not prove that they would burn up completely and not be a hazard to the public. So major design changes have had to be made in order to ensure that they could be valid for flight. So it's a very important issue. And then you were asking about the community in general.
The open source program.
Oh, the open source programming. Yes. So there's a greater interest in trying to develop flight software and operating systems that are open source so that the community can collectively get highly reliable systems as a result of sharing that experience. I would say we're not completely there yet because many of these systems carry very sophisticated real-time software platforms, but others don't. Others just run simple scripts to command the entire system. But the flight software is an area which requires greater attention and something that we'll be pursuing.
You have a question in the back with a green microphone?
Hi, my name is Anwar, and I'm not currently a member. My question is this the type of technology that is going to be used in the proposed Breakthrough Starshot project, for example?
You know, I am not familiar with the Breakthrough Starshot, but I can tell you that there are studies. In fact, I'll be participating in a week-long study early next month at looking at the role that small satellites can play for interstellar exploration. So there is actually a great interest in understanding what type of technology capabilities regarding propulsion and communication and observing sensors can be used to support interstellar science. I don't know if that's related to the breakthrough Starshot problem. I'm afraid I'm not familiar with it. But people are becoming very creative and trying to explore all avenues with what these systems can do.
For the sake of background information, I believe that the breakthrough Starshot is a proposal to take Gram-sized satellite space probes and accelerate them with laser beams from Earth or from the moon or from outer space to impart a very, very high speed to them over a long period of the laser beam impinging on them to get them to a nearby star in a reasonable amount of time. I think, what is it, a century at this point? Something like that.
Oh, well, thank you, Larry. I mean, I can say there have been other devices called CubeSats that have flown before, which are roughly 2 centimeters on the side. And the idea is that you can deploy many of them to make certain types of very quick, relatively local measurements in Earth's atmosphere. And who knows, maybe there might be a mechanism of advancing a technology of that kind in that context.
I think we'll give Frank the last question.
Frank Robert, a member. Sorry for shouting. On the background, further to what you were saying, Larry, I think that Starshot is using a synthetic aperture, a very tiny spacecraft, and possibly lensing, so that opens up to a lot of other discussions. But the question was on similar. You had said that there are a lot of efforts to increase the bandwidth coming from very small spacecraft, and that, of course, we know that optical is now starting to enter into the equation, after Laddie got 622 megabits from the moon. Yes. Are you aware of specific undertakings to get to very high bandwidths, and specifically optical?
Yes, there have been laser comm and optical communication experiments flown. In fact, just recently there was a NASA mission that demonstrated 200 megabits per second using optical comm, but there have also been other experiments as well performed by industry, and it's certainly a direction of near-term interest, provided the clouds don't get in the way. But yes, it's a very important capability. There's even thought about space-to-space optical comm work that might go on to support constellation observations.
Well, I said you were the last, but I guess I'll be the last. So this isn't really related to small sats, but on that subject, isn't there an effort at NASA to augment the deep space network using laser communication?
Yes, there is definitely research that's going on to support that. I mean, you could imagine what that capability would mean for high data rate transfer over long distances, and it's very active.
So with that, I think let's thank our speaker.
Well, thank you.
And it's wait, don't go off the stage. No, come back.
I will come back.
As a small token of thanks, we'd like to present you with this framed copy of the announcement of your talk.
Oh, this is wonderful. Thank you very much.
And also a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, published in probably June 1874, which
I'm
has
very honored to
a list
receive this.
of the original members and the original bylaws and why it was named the Philosophical Society of Washington. It wasn't to confuse us all. Thank you very much.
Oh, thank you very much, Larry. It's been my great pleasure.
Now, before we go, we have a few closing announcements, a few housekeeping things, and I'm going to tell you what the schedule is for the spring. Imagine that. So, PSW depends on its membership, and if you're not a member, we'd ask you to join. If you are a member, we ask you to consider giving a little more and also consider getting involved. It's easy to join if you want to. You just go to the home page and click on the big blue button up in the right-hand corner, which you can't see on this screen, which will take you to this screen. The big blue button says join. Press that button, you get to this screen, press on the membership application button. It will pull up a membership application. We'll ask you for some information. And when you get down to the bottom, we ask you to pay your dues. If you're not admitted, we will refund your dues. But it's most likely, if you're interested in science, that you will be admitted. and you can become a member of PSW, and we'll be very happy if you do that. If you have any questions about membership, you can ask our membership director, Lloyd Mitchell, over there, or our corresponding secretary, Robin Taylor, or our social media director, Ann McQueen. Having a social moment here. Don't get fooled by the PayPal announcements. You can pay by regular credit card. Just look for the button that says use your credit card or debit card. If you are a member and you haven't paid your dues, please pay your dues. PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code. Tax contributions are tax deductible to the extent permitted by law. Our next lecture and the 2,399th meeting will take place on November 2 at 8 p.m. right here in the Powell Auditorium. The speaker will be Steve Squires of Mars Rovers fame, among other things. He will be speaking on the proposed Comet Astrobiology Exploration Sample Return Mission, known as CESAR, a mission to bring back samples from the Comet 67P, with a long Russian name I won't try to repeat. It's an interesting talk for us because we just had a talk by Zibby Turtle on the proposed Dragonfly mission to Titan. So the Dragonfly mission to Titan and CESAR mission to return a sample of a comet are competing missions at NASA. And if you had shown up for both of these lectures, you would see the people primarily responsible for both of these missions, and you could track them through the NASA selection process and then follow whichever mission is chosen to its hopeful success. And I think that's in keeping with PSW's role, in part, as a gathering place for scientists to talk about the work that they're doing and the work that they're planning. And eventually, hopefully, they'll be able to come here and give us a talk on the work that they've done and what they found in this mission, whichever one is selected. And, you know, maybe we'll get lucky and Congress will decide to fund them both. All right, so the spring schedule is shaping up pretty nice. Our last talk of the fall will be Franz Cordova, director of NSF, and I'll be happy to tell you exactly what she's going to talk to as soon as she tells me. She'll be talking on December 7th. The President's lecture on Jan 11th will be given by Lee Cronin, who always talks about something interesting. Lee is an inorganic chemist with a wide range of interests. Lately has been interested in automating chemistry and using additive manufacturing, also known as 3D manufacturing, inkjet manufacturing, to create reaction vessels that are specifically designed to carry out certain kinds of reactions using a panoply of reagents that are chosen by an AI in order to discover new reaction mechanisms, which probably sounds a little dry, but he's also trying to create life from inorganic matter in a test tube. So he's always very interesting and stimulating. Now on Jan 25th, it is going to be either the rescheduled Venus lecture or a lecture on wearable biometric sensors. On February 8th, we have Raman Sundram of the University of Maryland, and he'll be speaking on supersymmetry and multidimensional spacetimes. Davey Bach will be speaking on February 22nd on neural mapping. He has a method for mapping every single neural connection in the brain of a, what do we call it, model organism. On March 8th, Ramesh Gopinath from IBM will be talking on blockchain, not blockchain and cryptocurrency, but blockchain used in commerce, which apparently is becoming a widespread practice in a variety of areas, from tracking agricultural products to securing financial transactions. March 22nd will be reciprocal to Jan 25th, either Venus or the wearable sensors lecture. April 12th, Mary Angela Lusante from Princeton will be talking about dark matter. And maybe by then she'll really know what it is. And on April 26th, we have Kim Janda from the Scripps Research Institute, who is trying to produce vaccines against drugs that are drugs of abuse. And then we have the Henry on May 17th, which we're hoping to have a very well-known figure in the robotics industry give us the talk. But he hasn't agreed, so I can't say. So with that, let me note that the social hour ends at 10:30, after which PSW members and their guests gather and go across the street to the Fairfax Hotel Lounge to continue the discussion and have additional libations. If you are not a member and you want to join us, please let us know. You're welcome to join us a couple of times if you're not a member. But this is a member's benefit, so we hope that the members will all gather with us over there. Please talk to Corresponding Secretary Robin Taylor, or Membership Director Lloyd Mitchell, or Social Media Director Ann McQueen if you're interested. Please use the side entrance to exit the building, and I will accept a motion from a member to adjourn the meeting to the social hour. And as usual, Bob is first up, and we have a couple of others, so all in favor? Aye. All opposed? Meeting is adjourned to the social hour.